Welcome to Philosophy with Xing, where we uncover the beauty behind philosophy. In today's episode, we'll be looking at a quote: "Scientific knowledge is simply a matter of agreement among experts," and we'll be crafting a response to this through a philosophical or epistemological lens. So, before we begin, let's highlight some key terms. Scientific knowledge, which is the area of knowledge that we're looking at, and we can ask ourselves, what is the nature of scientific knowledge and the methods of construction of scientific knowledge? Next, the use of the word simply could mean that it's only, or there's some kind of derogatory tone that is used to describe the nature of scientific knowledge. So is it true that scientific knowledge is simply a matter of agreement among experts, and these experts should be scientific experts, scientists? And the idea of a matter of agreement, there's this consensus among scientists. So does that mean that there's no objective basis for science? We'll be answering all these questions in our response to this quotation. Alright. If scientific knowledge was simply a matter of experts reaching a consensus, it would imply that the creation of scientific knowledge is based solely on shared assumptions, beliefs, and values held by the scientific community. So if scientific knowledge is simply a matter of agreement, then it would just be a bunch of scientists agreeing on some assumptions, beliefs, and values. However, in reality, beyond consensus, scientific theories need also be empirically tested with the external world to ensure they correspond with the physical environment for them to be regarded as knowledge. So remember this idea of knowledge. If we follow Plato's tripartite definition of justified true belief, we do need some form of justification and truth in this scientific claim in order to make this scientific claim be considered knowledge. So there is an empirical basis of science, which means that there is some sort of objective basis of science. Thus, while the creation of scientific knowledge by consensus allows for coherence across theories, branding beliefs as scientific knowledge just because they were attained by common consensus alone is insufficient. As such, I disagree with the statement that scientific knowledge is simply a matter of agreement among experts and put forth the notion that while consensus is necessary for theories to be considered scientific knowledge, the scientific method coupled with scientific experimentation and observation should also be employed. Consensus and empirical testing complement each other, and it is only with a combination of consensus and empirical evidence that scientific hypotheses can be termed as knowledge. So in my entire argument here, I am essentially saying that there needs to be a combination of shared assumptions, consensus, with the empirical basis of science in order for something to be considered scientific knowledge. So in my first argument, I would explain how and why consensus within the scientific community is necessary for theories to be considered scientific knowledge. So consensus is required for a claim to be considered scientific knowledge, SK for short. But consensus alone is not enough. Consensus within the scientific community is necessary for theories to be considered scientific knowledge. However, consensus alone is insufficient in creating scientific knowledge due to the flaws of consensus. Collective agreement among scientists is useful by the pragmatic theory of truth, as having a repository of shared knowledge that is regarded as the collective truth increases the productivity of scientific advancements. So why is it pragmatic for consensus to be used? Is to increase our productivity of scientific advancements. By agreeing on common viewpoints, scientists can proceed to research deeper into specific topics, thereby increasing our understanding of the workings of the external world. For instance, scientific definitions such as the fact that the standard enthalpy change of a reaction is when molar quantities of reactants, as specified by the chemical equation, react to form products at 1 bar and 298 K, which are regarded as the fundamentals of scientific knowledge, are collectively agreed upon by the scientific community. Upon establishing these definitions as scientific knowledge, scientists can proceed to build upon such definitions by deriving other theories, such as the Hess's law, which outlines the relationship between enthalpy changes of reactions. Agreement amongst experts also aligns with the coherence theory of truth, because viewpoints within the scientific community cohere with one another and form a web of justified beliefs that can be called knowledge. So there's this coherence theory of truth. As it is experts that propose theories, it is probable that their theories are not terribly flawed, given that scientific experts have expertise and a better track record in the area of science than lay people. So, by citing the pragmatic theory of truth and the coherence theory of truth, I explain how consensus is required. However, there are flaws to simply relying on consensus to construct scientific knowledge. Hence, consensus alone is insufficient in creating scientific knowledge. Given that consensus relies on a coherence across a web of beliefs with no need to reference the external independent reality, humanity as a collective is not necessarily getting closer to the objective truth in science. So over here, I'm saying there are flaws to consensus. The first being consensus is a web of beliefs. And we might not necessarily be getting closer to the objective truth. Purely relying on consensus also leaves science vulnerable to epistemic bubbles, especially within Kuhn's paradigms of science. According to Kuhn, scientists work within the parameters of a scientific paradigm, which is normal science, on a day-to-day basis. These paradigms have been agreed upon by the scientific community as truths after empirical verification proved it to be so. Thereafter, beliefs within the paradigm are regarded as truths and knowledge, and hence further experimentation is not needed to verify them. This may lead to inaccurate scientific theories being passed down across generations, thereby decreasing the legitimacy of science as a body of knowledge. As a paradigm, Newtonian mechanics corresponded with Earth's physical behavior, such as the path of Earth's orbit and gravity, through empirical verification. Because of the community's acceptance of this paradigm, there was little effort to propose other scientific theories to explain the same phenomena. Consequently, the body of scientific knowledge was limited to the workings within Newtonian mechanics. It was not until Einstein's theory of relativity, which was introduced in the 20th century, that scientists realized Newtonian mechanics could not accurately predict the orbital path of the planet Mercury, unlike Einstein's, thereby falsifying Newton's theories. Evidently, epistemic bubbles within paradigms take decades or even centuries to be rectified, and predictions and derivations based on false theories have to be re-evaluated, rendering science to be deemed as less legitimate during the process of re-evaluation. To mitigate issues arising from epistemic bubbles within paradigms of science, a peer review system has been put in place for checks and balances to ensure research done by scientists are objectively accurate. So we have a mitigating factor, fortunately, to this idea of epistemic bubbles and consensus being a web of beliefs, so mitigated by peer review. Let me zoom out so that everybody can see the essay plan so far. However, the possible lack of inter-reviewer reliability undermines the purpose of a peer review system. So although there's a peer review system, but there could be some kind of social character of science. This is inherently due to the social character of science, which Ludwig Fleck proposes to be how what constitutes scientific knowledge is merely what the scientific community has settled upon at that point. Thus, it suggests that science is not completely objective, but also dependent on the scientists involved, who are more often than not susceptible to personal biases. Inter-reviewer unreliability is primarily motivated by the vested political, social, and economic interests of certain scientists. Scientists, as individuals, could have social and political motivations to scale the ladder of hierarchy within the scientific community, to secure connections with important individuals for personal gain, or even to conform to societal norms applicable to the societal context at the time. So, Ludwig Fleck proposed the idea of a social character of science that could be a flaw of peer review. So even if peer review could mitigate epistemic bubbles caused by consensus, being a web of beliefs, peer review is also a victim of social character of science because the scientific community is inherently made up of humans who are very susceptible to certain like biases or even the social context at a point in time. For example, in the 15th century, the heliocentric model of the universe was first introduced by Copernicus as an alternative to the scientifically falsified geocentric model. However, although the heliocentric model more accurately encapsulated the behavior of the Milky Way, Copernicus faced strong opposition from the Church against the heliocentric model. It was only until the 16th century that the heliocentric model was accepted. Furthermore, in the current context, scientists may also be swayed by monetary incentives offered by companies involved in big science to support or oppose scientific hypotheses and become susceptible to confirmation bias. So peer review could also be susceptible to confirmation bias. Besides the allure of money from big science, intrinsically, it is in our human nature to desire to prove our own predictions right rather than wrong, even though observation may not correspond to the theories proposed. Thus, it is apparent that merely relying on consensus to create scientific knowledge undermines the importance of objectivity and truth of scientific knowledge. So, evidently, even if we try to mitigate the flaws of consensus, there are still flaws in the solution to mitigate the flaws of consensus. So, because of that, I brought in the idea of how, in totality, consensus alone is not sufficient. Because relying on consensus alone undermines the importance of objectivity and truth in scientific knowledge. Hence, empirical testing in the form of Popper's falsification and the hypothetical deductive method is crucial in upholding scientific objectivity of the independent external world. So my argument would be empirical testing is crucial in upholding scientific objectivity of the independent external world. Empirical testing complements consensus in creating scientific knowledge, as it brings scientific theories closer to the truth through correspondence, increasing reliability of scientific knowledge. In reality, scientific knowledge is not just based on consensus because it corresponds with the external world. So remember, for consensus, we talked about coherence, and now in empirical testing, we're talking about correspondence. By Putnam's no miracles argument, NMA, it will be a miracle if whatever scientific theories that have been predicted and agreed upon by the scientific community corresponds with the external reality if the theories themselves are not true. Hence, in order to bring scientific theories closer to the objective truth, theories should be empirically tested and verified. To do so, the hypothetical deductive method, which is the scientific method, is employed in forming scientific knowledge. The scientific method involves stages of hypothesis testing and empirical verification. Once a hypothesis is empirically verified that it corresponds to the external world, it is deemed as scientific knowledge. However, the scientific method has its demerits as it falls prey to Hume's problem of induction and underdetermination. So for correspondence, we're talking about the scientific method, but there are some flaws to it, including problem of induction and under determination. The problem of induction suggests that conclusions drawn from induction are unreliable as compared to conclusions of deductive arguments, as there are no certain grounds that what has been the phenomenon in the past will be the same as what will play out in the future. For instance, in Bertrand Russell's analogy of chickens, so we're talking about Russell's chicken analogy, a chicken has been fed every day since it was born and assumes it will be fed the next day, only to be slaughtered by the farmer. Under determination suggests that the amount of empirical evidence one has during experimentation is insufficient to indicate the beliefs one should hold towards the subject. For instance, empirical results which translate to data points plotted in a straight line graph does not necessarily indicate that the behavior of the experiment will follow a linear fashion across other points that are not tested. So what this means right over here is that if my plotted points are like this, it looks like a linear graph. If we try and draw a best fit line, it looks like it's a straight line graph. But this is usually our conclusion. However, there's also another alternative to drawing a line through the data points, which could be this. Notice that my graph is also passing through all the points. So the idea of underdetermination is that there is not enough empirical data to properly extrapolate or infer a relationship between the data points and the variables in question. Unless your data points are really, really small. Unless you have really, really small data points along the entire line of the graph for you to understand that, oh, this is the relationship between the two variables in the scientific experiment. But even so, if we had really, really close data points so that we can plot a somewhat accurate graph, if we were to we can also argue that if you were to zoom in into greater detail between the close data points, there are also lots of spaces in between. And we could also draw the graph this way. So again, we could never really be absolutely certain that our data points really correspond to certain scientific phenomena or relations that we have induced from the graph or deduced from the graph. Due to these reasons, while the scientific method brings us closer to the objective truth in science than consensus, it is not entirely objective, as the conclusions made do not necessarily accurately reflect phenomena in the external mind-independent world. Falsification, hence, is a solution to the flaws of the scientific method, proving to be a viable method of achieving objectivity in scientific knowledge. So, okay, given all these problems with the scientific method, the traditional Baconian scientific method with the hypothetical deductive method, there's flaws to all this because, we talked about the problem of induction, we talked about underdetermination, so a mitigating factor or mitigating theory would be Popper's falsification. To mitigate the problems of the scientific method, which is purportedly objective but contains inherent flaws, an alternative method of empirical testing is employed, such that scientific knowledge is not only dependent on consensus, but also on correspondence with the external world. Popper proposes falsification as a method to weed out hypotheses that do not correspond to the external world through empirical experimentation and testing. Popper acknowledges the problem of induction that we can never be logically certain of what actually is, but we can be sure of what is not through falsification. Thus, falsification works around the problem of induction. Falsification can also be employed more easily than verification, as the discovery of one anomaly falsifies a theory, while having many observations which correspond to the theory does not necessarily mean that the theory holds true, as there might be a possibility that the anomaly has not been found yet. This is analogous to falsifying the claim that all swans on Earth are white. As long as one finds a black swan, one can be sure that not all swans are white, as opposed to finding many white swans with no black swans, as there's a possibility a black swan exists that has not been discovered yet. Consequently, scientific beliefs formed through falsification are justified by reliabilism, as the belief was formed through empirical testing, which makes it a reliable method, and true as it corresponds with reality, making it scientific knowledge. However, while scientific knowledge is generally created by empirical testing and consensus, there are certain exceptions where the question of whether science is simply a matter of agreement among experts, as suggested in the quotation, depends on the nature of scientific knowledge. Consensus between experts can be on norms, concepts, and theories. Norms are the socially accepted methods of scientific experimentation and skills needed within science, such as the need for empirical verification in order to prove a scientific theory. Norms are largely accepted by the scientific community with little contention. Conversely, expert agreement on concepts, such as whether light is a wave or a particle, as Einstein proposed, is more contentious, as scientists have changed their consensus on such top concepts over time due to technological and scientific advancements. Scientific theories are most contentious, as expert agreements on theories such as the phlogiston theory in chemistry have changed dramatically over time. The general scientific consensus that a fire-like element is released from combustible bodies during combustion is taken to be true in the distant past, but that theory has since been completely discredited and replaced by new chemistry theories. Evidently, more fundamental statements such as scientific norms and definitions of scientific terms enjoy more consensus within the scientific community and are taken to be scientific knowledge, while less fundamental statements such as concepts and theories, which build upon the definitions of scientific terms and methodologies, cannot be judged on its degree of truth purely based on the consensus of the scientific community. As such, scientific knowledge is generally created by consensus and empirical testing, but some types of scientific knowledge rely more on consensus than others. To conclude, scientific knowledge is not simply a matter of agreement among experts, going back to our quote at the top of this page. As empirical testing and verification that the theories postulated correspond to the external world are necessary for theories to be counted as knowledge, as scientific knowledge. Ultimately, what truly distinguishes science from the rest of the areas of knowledge is that the workings of science require empirical testing and correspondence with the external physical world in the creation of knowledge. Yet, ironically, while science is considered one of the most objective areas of knowledge, it is simultaneously susceptible to biases because the nature of science necessitates a scientific community, which is made up of humans who are inherently biased. Perhaps this is an indication that regardless of the area of knowledge, the knowledge created will never truly be absolutely representative of what the reality actually is. And to me, it is this uncertainty that confers beauty to knowledge. Alright, that marks the end of today's episode. Hope that you enjoyed it. Thank you and goodbye.